Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to start the inner transition elements, F block. Last class I have discussed D block. The F block consists of the two series, lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinium. Because lanthanum closely resembles the lanthanoids, it is usually included in any discussion of lanthanoids for which general symbol is Ln, lanthanum, Ln. Similarly, a discussion of actinoids includes actinium besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than do members of ordinary transition elements in any series. They have only one stable oxidation state, and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. Again, I will want to tell you, they have only one stable oxidation state, and their chemistry provides an excellent opportunity to examine the effect of a small change in size and nuclear charge along a series of otherwise similar elements. The chemistry of actinoids is, on the other hand, much more complicated. The complication arises partly owing to the occurrence of a wide range of oxidation states in these elements, and partly because their radioactivity creates special problems in their study. There are two problems, or you can tell this chemistry of the actinoid is, on the other hand, much more complicated. Why complicated? Then first reason, the complication arises partly owing to the occurrence of a wide range of oxidation states. Actinoid series has more oxidation state. Their members have more oxidation state. This is the first cause for complication. And second, because their radioactivity creates a special problem. They have reactivity properties, hence this creates problem in their study. The two series I will discuss one by one. The lanthanoid series. Now I am going to discuss lanthanoid series. The names, symbols, electronic configuration of atomic and some ionic states, and atomic and ionic radii of lanthanum and lanthanoids, for which the symbol Ln is used, I will discuss. Okay. First, I will discuss electronic configuration. Electronic configuration of lanthanoids series. It may be noted that atoms of these elements have electronic configuration with 6s square common, but with a variable occupancy of 4f level. However, the electronic configuration of all the tripositive ions, the most stable oxidation state of all the lanthanoids, are of the form 4Fn, a small n, 4F. Okay, n is equal to 1 to 14, 4Fn, where n is equal to 1 to 14 with increasing atomic number. Then here outer electronic configuration, it ends with 6s square. This is common, but with variable occupancy of 4f energy level. Now I want to discuss atomic and ionic size. The overall decrease in atomic and ionic radii from lanthanum to lutetium. Starting is lanthanum, first member is lanthanum and last member is lutetium. This is called actually lanthanoid contraction, decrease in atomic size and atomic radii. The overall decrease in atomic and ionic radii from lanthanum to lutetium, this is called actually lanthanoid contraction, is a unique feature in the chemistry of lanthanoids. It has far-reaching consequences in the chemistry of third transition series of the elements. The decrease in atomic radii derived from the structure of metals is not quite regular as it is regular in M3+. Again you listen. The decrease in atomic radii derived from the structure of metals is not quite regular as it is regular in M3+ ions. M means metal ions. This contraction is of course similar to that observed in ordinary transition series and is attributed to the same cause. The imperfect shielding, why it happens, contraction that I am telling you. The imperfect shielding of one electron by another in the same subshell, that is the main reason for contraction. Okay, lanthanoid contraction. The imperfect shielding of one electron by another in the same subshell, this is the main cause for lanthanoid contraction. However, the shielding of one 4f electron by another is less than 1d electrons by another with increase in nuclear charge along the series. This shielding of one 4f electron by another is less than 1d electron by another, means here in D shielding is more. In D orbitals or energy level shielding is more, but in 4f shielding is not proper. 4f electrons, shielding in 4f electrons, many electrons are there, they are not shielding properly. Okay, then 4f electrons, actually here shielding is less than D electron. In D electron, they are many electrons are there, D up to it can go up to 10 electrons, then they are shielding properly. But in F, shielding is not properly, it is a less shielding. That's why nucleus is attracting electrons and size decreases, and due to D electrons size increases, but due to the 4f size decreases, hence finally both cancel the effect and little you can say this increased size due to less shielding in D electrons is neutralized by improper shielding of 4f electrons. Okay, and this happens by with increase in nuclear charge along the series. There is a fairly regular decrease in the size with increasing atomic number. The cumulative effect of the contraction of the lanthanoid series known as lanthanoid contraction. What will happen? What will be the consequence of lanthanoid contraction? Then lanthanoid contraction causes the radii of members of the third transition series to be very similar to those of corresponding members of the second series. Means radii of both third series and second series becomes equal, almost equal. Okay, this is the consequence of lanthanoid contraction. Again, I am telling you that consequence of lanthanoid contraction, it causes the radii of the members of third transition series to be very similar to those of corresponding members of second series. The almost identical radii of zirconium Zr, it is 160 picometer, and hafnium 159 picometer, both are almost equal. This is a consequence of the lanthanoid contraction. Okay, a consequence of lanthanoid contraction account for their occurrence together in nature and for the difficulty faced in their separation. Now, this both members can't be separated, means series 2 and series 3 transition metals can't be separated because their properties are very similar. Size is also very similar. Now, I want to discuss oxidation states. Oxidation states of lanthanoid series, members of lanthanoid series. In the lanthanoid, lanthanum third, lanthanum La, lanthanum third, and Ln, La third and Ln third compounds are predominant species. Means in lanthanoids, La means lanthanum, and Ln is a lanthanum. It is actually La term is for lanthanum, and generally it is discussed with general symbol is Ln. Ln is a generally it is represented by Ln. Okay, then in the lanthanoid La and Ln third, La third means Ln third, you can tell Ln third compounds are predominant. It is found in large scale or predominant species. However, occasionally +2 and +4 ions in solution or in solid compounds are also obtained. Means +2 and +4 ions in solution or in solid states are also available. This irregularity arises mainly from the extra stability of empty, half-filled and fully filled F subcell. Why this irregularity means +3 you are getting, +2 also and +4 also, but generally +3 is common. Then this irregularity arises mainly from the extra stability of empty, half-filled or fully filled F subcell. Okay, this is due to extra stability. Extra stability of empty means D is equal to F is equal to 0. F is equal to 0. F has no electron. Half filled means F have 7 electron. Actually maximum capacity is 14 electrons. Then due to this irregularity is due to the extra stability of empty, half filled or fully filled F subcell means F14. Thus the formation of cerium-4 is favored by its noble gas configuration. In cerium-4 it is favored. Why? Because of its noble gas configuration. But it is a strong oxidizing agent. But it is a strong oxidant reverting to the common +3 state. It comes to +3 state also. The standard electrode potential for cerium Ce4 oblique Ce3 plus Ce4 plus oblique Ce3 plus is 1.74 volt. This is the standard electrode potential value for cerium-4 to cerium-3 plus, which suggests that it can oxidize water. This standard electrode potential suggests that it can oxidize water. However, the reaction rate is very slow and hence cerium-4 is a good analytical reagent. Now PR, ND, TB and DY also exhibit +4 state. Actually first I will tell the name. Now we will not understand symbol. Let me tell a name of the members of lanthanoid series and symbol. Then you will understand. Actually lanthanum La, that is the first member, 57. Lanthanum is the first member of lanthanoid series. Okay. Then lanthanum is La, symbol is La. Cerium is Ce. Praseodymium PR, P and a small r. Praseodymium. And this neodymium means ND. ND is called neodymium. And PM is called promethium. Promethium symbol is PM. SP and capital P, small m. All are like that. First letter is capital, other is small. Then neodymium means ND, promethium, PM, samarium is SM, europium, EU, gadolinium, GD, terbium, TB, disoprosium, DY, holmium, HO, erbium, ER, thulium, TM, ytterbium, YB, lutetium, Lu. Okay. Now you will understand the symbol. Then I was discussing that a standard electrode potential value for cerium 4 oblique cerium 3 plus, cerium 4 plus oblique cerium 3 plus, its value is, standard electrode potential value is plus 1.74 volt, which suggests that it can oxidize water. However, the reaction rate is very slow, and hence cerium 4th is a good analytical reagent. PR, ND, TV, and DY. Promethium, neodymium, thulium, dasopodium also exhibit plus 4 state, but only in one oxide. Okay. MO2, M means metal oxide I am talking about, MO2. Okay, this plus 4 state it is showing in PR, ND, TV, DY. These exhibit plus 4 state, but only in oxides, that is the MO2. M is the metal. MO2 have plus 4, and EU2 plus europium ion, EU2 plus is favored by losing the 2 electrons, and its F7 configuration. After losing 2 electrons, it gets F7 configuration. This accounts for formation of this ion. However, EU2 plus is a strong reducing agent, means it can give the electron. Okay, EU2 plus is a strong reducing agent, changing to the common plus 3 state. Okay, similarly, ytterbium, YTTERBIUM, YB, ytterbium. Similarly, ytterbium 2 plus, which has a F14 configuration, is a F14 means obviously it will be stable. Then YB plus, which has F14 configuration, is a reductant, means a reducing agent. Thulium, TB. Thulium has half-filled F orbitals. These questions are, all three questions is asked. Okay, TB 4th has a half-filled F orbitals and is an oxidant. Thulium 4th has half-filled F orbitals and is an oxidant. And here ytterbium YB2 plus, which has F14 configuration, fully filled, is a reductant, reducing agent, and TB 4th is a half-filled F orbital and is a oxidizing agent, means oxidant. The behavior of samarium is very much like europium. Okay, behavior of samarium, that is the SM, samarium, is very much like europium, exhibiting both plus 2 and plus 3 oxidation state. Samarium is like europium, exhibiting both state, plus 2 and plus 3 states. Now I want to just discuss these things ready in picometer. Okay, and their electronic configuration. Lanthanum La, its electronic configuration is 5d1 6s square. 5d1 6s square. Now you can understand that 5d1, 6 square is there, 6s square. Then 3 electron is possible that can be removed. Then it is easy to remove 2 electron. First 6s square, that electron can be removed. Hence ln in general, lanthanoids we are expressing with ln 2 plus ln. Then here if 2 electron will be removed, then it will form ln 2 plus. Ln electronic configuration, that about the lanthanum La, it is 5d1 6 square. If this 2 electron is removed, then it will form ln 2 plus. And now only 5d1 will remain. And in this, in lanthanum 3 plus, ln 3 plus means 1 more electron should go. If now for ln 2 plus 2 electron gone, 6s square, last orbit, that electron gone. Then now only 5d1 was remaining. Now for 3 plus 1 more electron should go. Then now 5d1 will also go. Then what will remain? 4f0 will remain. 4f0 will remain. Okay. Then lanthanum actually radius is 187. Okay, in picometer. 187 picometer. It is a radii for lanthanum Ln. But if you will consider lanthanum ion, 3 ion is common, Ln 3 plus. Then what is its radii? Then its radii became very less, 106. Now you can see Ln was having 187. Now Ln 3 plus lanthanum, in common way I am talking about lanthanum. Now it became 106. So much difference in radii. Now same way cerium, Ce, its electronic configuration is 4f1 5d1 6s square. In 4f1 1 electron is there. In 4f1 1 electron is there. 5d1 1 electron is there, and 6s 2 electron. Now same way that 4f lanthanum 2 plus if you want, then if 2 electron will go from the 6s square, then what will remain? 4f1 1 electron and 5d1 1 electron. And if suppose 5d1 electron comes to the 4f, then 5d will be 0. Only 4f2 will remain. 4f 2 electron, that will remain for 2 plus, Ln 2 plus. Okay. If you want to write Ln 3 plus, then now only 4f1 will remain. 4f1 will remain. And if Ln 4 plus you want, means 4 electron wants to remove, Ln 4 plus, then this what is the 1 electron is remaining now, that will also go. Then we will get Ln 4 plus, and 4f0 will remain. Then now here for cerium radii is 183 for cerium, but Ln 3 plus, then it will come very less, 103. Like that way, praseodymium Pr, its electronic configuration is 4f3 6s square. There is no D, okay, no 5d. 5d is 0 because 4f3 is there. 4f3 is there. That 1 electron came to the f. That's why 4f3 5d is 0, means nothing. Then 4f3 6s square is there. Then if you want to remove 2 electron, means you want Ln2 plus oxidation state, Ln2 plus, then now only 4F3 will remain. And if you want to make Ln3 plus, then one more electron will go, then 4F2 only will remain. 4F2 will remain. If you want to remove one more, means Ln4 plus you want, then now 4F1 will remain. Okay. And for praseodymium means PR, it's a lanthanum, means it's a radii is 182. In general we are telling Ln. All members are called Ln only, capital L, small n, Ln, lanthanum. All members of the lanthanum series is called Ln. Then now 182, that is for PR, praseodymium ionic radii. But lanthanum 3 plus, now it became further less, 101. Okay. Now next is Nd, neodymium. Then here electronic configuration is same way. 4F3 was, now it became 4F4, 6s square, correct? And like that way, same way, if you want to Ln2 plus 2 oxidation, or Ln2 plus, then that 6 square that will go, then 4F4 will remain. 4F4 will remain. And if you want to remove one more electron to get Ln3 plus, then now 4F3 will remain. And again, if you want Ln4 plus, then one more electron should go, then 4F2 will remain. And now for neodymium, its radii is 181. But Ln3 plus, when you will remove 3 electron, then now radius will be very less, 99 only picometer. Like same way, promethium, PM is 4F5, 6s square. Then same way what I told, if you want to get a 2 plus, Ln2 plus, then 2 electron bit will go. If 3 plus, then one more electron will go, then 4F3 will remain. Okay. Then in everywhere same thing will happen. And it's a radii, you can see, PM, promethium, 181. Its radius is 181, and Ln3 plus is 98. Now samarium, samarium, 4F6, 6s square. One electron is going to the F, that you keep in mind. 4F, 6s square. Now same way, this is now contraction started. Now it become 180. Ln is 180 and lanthanum 3 plus is 96. Now europium, EU, means 4F7, 6s square. One electron is increasing. Then now again you can say contraction, I told you started. Now it became these things. 180 I told for samarium, 180, and 96 was Ln3 plus. But here in this case europium, it is 4F7, 6s square. Then this is a stable, extra stability, 4F7. Then now here you will get now more, 199 Ln. Ln means radii 199, and for Ln3 plus it will get 95 less. Now same way gadolinium, GD. This is a 4F7, 5D1, 6s square. Now because 4F7 is there, then it is a new electron is going to the D, not to the F, because it is extra stable. Then now again this will make plus 3 very easily. 5d1 and 6 extra easily they can lose. Okay. Then here you will get this thing called D already started. 1 electron came in D. That's why again it became less. Radius became less, 180 only. And 3 plus, ln 3 plus means 94. You see how contraction is going on. Now again further contraction you see in the case of terbium, TB. Then TB now new electron in this TB, new electron. Now actually it should go to the D2, but now that 2 electron and 7 electron, now directly it is going total 4f9. F was 7 and D1 was there. Then now they have taken, F has taken that electron also, a new electron also. Then now it became 4f9, 6s square. And now here again contraction started. Contraction 178. You see how it started from 187. Now it is 178 contraction. And for this, what is the plus 3 accident? ln 3 plus is 94. Then this gadolinium, actually gadolinium was having 94. Now actually this terbium was 178. Now 178 terbium, but in ln 3 plus that is a 92. See how much decreased? It decreased. ln is 178, but ln 3 plus is 92. Like that way, dy, disoprosium. Then now 1 electron, new electron will go to the F. Now it becomes 4f10, 6s square. Then now in this case, again decreased. Radius decreased. Contraction 177. And this also reduced 91, ln 3 plus. When it will decrease, this will also decrease. Both will decrease. Now after that, HO, holmium, HO. Now 1 new electron came, 4f11, 6s square. Then now again you can say decreased, radius decreased, 176. 176, helium is 176 radius. But now ln 3 plus is 89. See, both are becoming less in comparison to the first one, means lanthanum. Now next is erbium, ER. Then now new electron enter to the F. Now it became 4f12, 6s square. And now this further reduced. Radius further reduced, 175. Erbium has 125 picometer radius. And this also decreased, 88. ln 3 plus is 88. Now come to the thulium, TM. Then now new electron again it will go to the F. Now it became 4f13, 6s square. Then now again further decreased. This erbium further decreased, 175, and ln 3 plus is 88, further decreased. Now thulium, I told you 13, then there now radius decreased 174, and ln 3 plus became 87, means after removing 3 electron it became 87, further decreased. Now ytterbium, YB, 1 more electron will come, then now it become 4f14, fully filled, 4f14, 6s square. Then now it's actually this also decreased. 173, and this ln 3 plus is 86. Now lutetium, Lu, lutetium. Now it is a new electron will come, then now it is 414 5d1, then now its contraction is not known. Okay, then this I have discussed about the these things, electronic configuration, outermost orbit electronic configuration I told you, and radius how it is decreasing I told you, and Ln3 plus means after removing 3 electron what is the radius that I have discussed. Now general characteristics I want to tell you of lanthanum series. General characteristics. This is all are important actually. Question is asked. Means related to this electronic configuration also question is asked. Related to radius question is asked. What is lanthanoid contraction and what is its consequence? These two questions are asked. Generally these two questions are asked, other questions are also asked. And now I am going to discuss general characteristics. All the lanthanoids are silvery white soft metals. All the lanthanoids are, lanthanoids means Ln in general, and La is lanthanum, don't forget. La means lanthanum and Ln means just in a general way their members, all members are called in general Ln, lanthanoids. Okay, then Ln, all the lanthanoids are silvery white soft metal and tarnish rapidly in air. Okay, it is a silvery white but tarnish rapidly in air, means color will fade, it will go. The hardness increases with increasing atomic number. This you remember. The hardness of lanthanoids increases with increasing atomic number. Samarium being steel hard, steel, iron and steel, that hard, means samarium is hard like steel. See how much hard is there, samarium being steel hard, very hard. And in general lanthanoids I am talking about, their melting points range between 1000 to 1200 Kelvin. Melting point, MP. Okay, their melting points range from 1000 to 1200 Kelvin. But samarium, because it is very hard, its melting point is 1623 Kelvin. And in general I am talking about lanthanoids. They have typical metallic structure and are good conductors of heat and electricity. Why they are good conductor of heat and electricity? Because you have seen in the last orbit 6 square is there, 5d is also there. They can lose the electron easily, they can form the ion, and they will, and it will convert to the ion and it is losing electron. That's why it can conduct electricity and heat. Okay, density, come to the density and other properties change smoothly. Exception is for europium and ytterbium. Okay, density and other properties are properties change smoothly. Exception is europium and ytterbium, and sometimes samarium and thulium, samarium and thulium also it happens. Means with four elements is an exception. Many trivalent, means +3, many trivalent lanthanoids ions are colored both in the solid state and aqueous solution. Means if you will dissolve this metal, lanthanoids ions, if it is present in either in solid or in aqueous solution, it is colored solution. I have shown you this different type of color. I have already. I have sent the color. Color of these ions may be attributed to the presence of F electrons. Just like D electrons, they will show colored. They will show colored ions. Same way here, color of these ions may be attributed, means due to. Okay, color of these ions may be attributed to the presence of F electrons. Neither lanthanum 3 plus La3 plus nor Lu3 plus ion show any color, but the rest do so. Here exception is there. Question is asked. Neither lanthanum La3 plus nor Lu3 plus, these two ions does not show any color. Neither lanthanum 3 plus nor Lu3 plus ion shows any color, but the rest do so. However, absorption bands are narrow. Their absorption band, if you will observe, then they will be overlapping like that, very narrow, very close. If not overlapping, then they are very close. Absorption bands are narrow, probably because of the excitation within F level. Electrons will be excited within F level. That's why they are very close, very narrow. The lanthanoids ions other than the F0 type, who are the members have F0? Then lanthanum 3 plus and cerium 4 plus. Both are F0 type. The lanthanoid ions other than F0. Other than F0 means La3 plus and cerium 4 plus. And the F14 type. F0 type means lanthanum 3 plus cerium 4 plus, and F14 type means Yb2 plus and lutetium 3 plus. Okay, these four elements are in exception. The lanthanoids ions other than F0 and the F14 type are all paramagnetic. Question is asked. These four are not paramagnetic. Lanthanum 3 plus, cerium 4 plus, that is a F0 type, and F14 type, ytterbium 2 plus, lutetium 3 plus. Except these four, all are paramagnetic, means it can be magnetized soon. The paramagnetism rises to maximum in neodymium. Again, further question, important question. Okay, the maximum paramagnetism is in neodymium. Okay, the paramagnetism rises to maximum in neodymium, and you know paramagnetism is due to the number of unpaired electron. More the number of unpaired electron, more the paramagnetism. Okay, already I have discussed. The first ionization enthalpy of the lanthanoids are around 600 kilojoule per mole. Ionization energy, also called ionization enthalpies. The first ionization enthalpies of the lanthanoids are around 600 kilojoule per mole. The second, again obviously it will be more. The second about 1200 kilojoule per mole, double, comparable with those of calcium. In case just will compare with calcium, then it is very high. Okay, and third ionization enthalpies indicate variation actually is there in third. The third ionization enthalpies indicate that high values exchange enthalpy concentration 3d orbitals of the first transition series. Okay, it can be compared with that. Actually, these things. Third, I am talking about a detailed discussion of the variation of third ionization enthalpies indicates that exchange enthalpy is there, already told you. Exchange enthalpy consideration as in 3d orbitals of the first transition series. I have told you here also exchange enthalpy, exchange energy, you can tell. Same thing, exchange enthalpy consideration is also here. And completely filled orbitals, F level. These two things are considerable for very high value for third ionization energy. Okay. This is indicated from abnormally low value of third ionization enthalpy of lanthanum, gadolinium and lutetium. These are an exception. Actually, here again I am telling you that exchange enthalpy consideration. Exchange enthalpy means exchange energy considerations as in case of 3d orbitals of first transition elements. Here also appear to impart a certain degree of stability to empty, half-filled and completely filled orbitals. Three cases are there. Always in three cases it will fill stable, means empty, means F is equal to 0, half-filled F7 and completely filled F14. Then these some degree of stability is there in case of empty, half-filled or completely filled orbitals of F level. And due to this is indicated from the abnormally low value. Why some third ionization enthalpy like lanthanum, gadolinium and lutetium, they have low value. Then for these things I told you, F0, F7 and F14 are responsible. Now come to the chemical behavior. In their chemical behavior, in general, the earlier members of the series are quite reactive, similar to calcium, but with increasing atomic number. They are quite reactive, similar to calcium, but with increasing atomic number. They have they behave more like aluminum. Again, I want to clear it. In their chemical behavior, in general, the earlier members of the series, means lanthanoid series, are quite reactive, similar to calcium, but with increasing atomic number. They behave more like aluminum. Okay, they also behave like aluminum in increasing atomic number. Now come to this standard electrode value E value for standard electrode potential for the half reaction. Lanthanum 3 plus 3 electron, that is the reduction, it will give LNS in general. In general, Ln means lanthanoids. I am talking about members of lanthanoid series, Ln. Then in general, Ln 3 plus 3 electron, it will convert to Ln metal, solid metal. And what are their values? Then its range from, means electrode potential range from minus 2.2 to minus 2.4 means its range is from minus 2.2 to minus 2.4, 0.2 volt difference. Okay, except for uranium. Uranium is in exception, for which the value is 0.20. 0.20. Okay, this is of course a very small, not very small, a small you can tell. This is of course a small variation. The metals combine with hydrogen, all metals I am talking about, the metals combine with hydrogen when gently heated in the gas. Okay, in gaseous form it will react. The metals combine with hydrogen when gently heated in the gas. The carbide means Ln3C, Ln2C3 and Lnc2. There are three carbides, Ln3C, Ln2C3 and Lnc2 are formed when the metals are heated with carbon. They liberate hydrogen from dilute acids. Remember, all lanthanides, they liberate hydrogen from dilute acids and burn in halogen to form halide. Means it will form halide with reaction with halogens. They form oxide also. They form oxides M2O3 and hydroxide MOH3. I told you plus 3 is common. Then that's why it is forming M2O3 as oxides and hydroxide MOH3. The hydroxides are different compounds, you can tell. Hydroxides are different compounds, not just hydrated oxides. Okay, it is different compounds, not just hydrated oxides. And also these lanthanides are basic like alkaline earth metals. This you remember. They are basic like alkaline earth metals, oxides and hydroxides. This question is asked. Lanthanides are basic like alkaline earth metal oxides and hydroxides. And their general reaction I can tell you easily. Lanthanum, Ln when it reacts with acid, it liberates hydrogen. First reaction. Second reaction, when it reacts with halogen, it forms LnX3, means lanthanum halide. When it reacts with water, lanthanum when reacts with water, it forms lanthanum LnOH3 plus H2. When it reacts with carbon at 277 Kelvin, it will give LnC2, lanthanum carbide. When it is heated with nitrogen, it gives lithium nitride, Ln. When it is heated with sulfur, it gives sulfide, means Ln2S3. And when it burns in oxygen, it gives Ln2O3, oxides of lanthanum. Now I am telling you use. The best single use of the lanthanides is for production of alloys steel. Alloys steel for plates and pipes. You know. That's the best single use of the lanthanides. That is, it is used for the production of alloys steels for plates and pipes. A well-known alloy is MISCHMETALL. MISC metal double L is there. MIS CHME. miskemetal, you can say miskemetal, which consists of lanthanoid metal 95% and iron 5%. Okay, misc metal, that is called misc metal. Double L is there, not metal, metal, which consists of lanthanoid metal 95% and iron 5% roughly, and little traces of sulfur, carbon, calcium and aluminum may be present there. Okay, main is the lanthanoid 95% and 5% roughly iron. This is called miskemetal, and in this traces of sulfur, carbon, calcium and aluminum are present. A good deal of miskemetal is used in magnesium-based alloy to produce bullets. Bullets, you might have heard the name. That is, their miskemetal is used. Miskemetal is used in making the bullets. Okay, bullets. Okay, or cell, you can say bullet cell. And here magnesium is used, magnesium based alloy, just like iron based. This miskemetal is used in Mg based alloy, magnesium based alloy, to produce bullet cell and lighter flint, and in lighter flint also. Mixed oxides of lanthanoids are employed as catalyst. Okay, as a catalyst, is main usage as a catalyst. The mixed oxides of lanthanoids are employed as catalyst in petroleum cracking. In petro industry it is used. Some individual Ln oxides are used as phosphorus in television screens. This I understand. Some individual lanthanum oxides, some lanthanum oxides are used as phosphorus, not phosphorus, phosphorus in television screen and similar fluorescing surface. Okay, fluorescing surface, in that also this is used. Two uses are there, special use. That is, individual lanthanum oxides are used. First, special use I am talking, that is as phosphorus in television screen, and second, similar oxides are used in fluorescing surface, FLUR, fluor, SCINC, fluorescing surface. Okay, then this I have discussed about lanthanoid series, and I have finished it. Next class I will discuss actinoid series. Thank you.